Now that we've looked at how to build a parser abstractly, we're going to go ahead and take a look at how we're going to build the parser for the interpreter that we're putting together. So the first thing that we're going to do is take a quick look at this module called Parsec, which is what we're actually going to use to implement our interpreter. So Parsec is a library that comes with the Haskell platform, and we can import it as text.parsercombinators.parsec. And it has some neat features in expression parsing that we'll be able to get later, and the import line to be able to do expression parsing is text.parsercombinators.parsec.expr. So the way Parsec works is it lets us combine little parsers into bigger parsers. And once we've combined all the little parsers that we need together, we'll get the actual parser that we want. So let me give you an example here. So parsers in Parsec are functions. And you pass some functions to some other functions to build your bigger parser. So if we want to parse a number, we can build a parser called number by combining the many-one parser combinator with the digit parser. So what this is doing is the digit parser matches a number, an ASCII character, 0 through 9. And the many-one combinator says that we have to match one or more of whatever we pass it as an argument. And so the number parser, therefore, is a parser that matches one or more digits. Let's go ahead and see that in action. So if I start up GHCI on this Parsec test file, Parsec gives us a function called parse, which takes a parser as an argument. So we're parsing a number. And then the next argument is the error string if this fails. So I'll just call that error. And then the final argument is the string that we're trying to parse, so 123. So we called parse number, gave it an error string, and gave it an input of 123. And it gave us back this answer, rate 123. In order to explain what's going on here with the rate, let me show you what happens if I'm like, parse the word bacon, which is clearly not a number. So the return value that we get there is left error, which was the error string. And then it gives us some feedback about exactly what went wrong in trying to parse that text. At line 1, column 1, the letter B is not a digit, which is exactly the error that we would expect from that test. So the neat trick that's going on here is that we have this structure called either, which can be right or left. And what Parsec is using either for is to make an error be something that we can pattern match that's different from a successful outcome. So if we get right, that's a success. And if we get left, that's an error. And when we get a success, the parser returns the value that it matched. Or you can specify your own value. Let me give an example of that. So let's go ahead and create a parser called 3numbers, which is the same type. And this type string is a little bit complicated. We need to include it to make Haskell not puke, but understanding exactly what it means isn't all that essential. The one important thing here is that it's two important things, is that it is a generic parser, and the return value is a string. So actually, we're parsing 3 numbers. Let's go ahead and return a list of numbers. So 3 numbers means we need to match a sequence. To match a sequence, we use do notation. And in Haskell, when we're using do notation, which normally denotes something that's going to happen in a sequence, we can either put things in curly braces and then separate things in sequence by semicolons, or we can put things one on each line. And then the new lines in the indentation will separate things for us. I'm going to do new lines and indentation because it's a little bit clearer. So the first number is a number. Then we have 0 or more spaces. Then the second number is a number. Then we have 0 or more spaces. Then the third number is a number. Then we have 0 or more spaces, and then we have the end of the string. And then the value of this parser when we run it is going to be a array, or a list, of n1, n2, and n3. So let's go ahead and see if I managed to type that correctly. So we'll load up Parsec test. Okay, so I did not manage to type that correctly, which is good, because this gives a good example of what's complicated here. The problem is that the thing that the number parsers gave us were strings, and the value that we specified for the 3 numbers parser was that it returned a list of integers. So let's go ahead and fix that. And we're going to fix that by making it so that the number parser actually returns an integer, because that makes sense. But the parser that's returned by many one digit returns a string. So we're going to have to do something a little bit more complicated. We're going to have to say that we're going to read that into an integer. And let's see if that compiles. It doesn't. That doesn't compile because the return value of read is not whatever this ridiculous type is. So we're going to have to go ahead and use do notation. So first we're going to read the digits into NN, and then we're going to return the result of reading NN as an integer. I'm just going to go ahead and assume that the precedence on that is wrong. Change the parens, and have everything work. Beautiful. So now when I parse 3 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, it in fact gives me back a list of 3 numbers. So let's go ahead and take a look at the actual parser that we're going to be using in the interpreter. So here we have the parser. We're loading the same 2 packages. Then we're defining this data structure. That's the thing that we're actually returning from the parser, an abstract syntax tree. The abstract syntax tree has 2 basic cases. Either we're a leaf, in which case a leaf is a number represented by an integer, or we're performing some operation. We have 4 binary operators, and we have 1 operator which is unary negation. A number is many one digit, 1 or more digits, just like the example. It can be followed by some spaces. And instead of just reading the number as an integer, we construct a calc_expr structure and then return that. And the return value of our parsers here are calc_exprs. We've got some other rules here. An operand for an operator is either a parenthesized expression or a number. A parenthesized expression is an open paren, an expression, and a closed paren. One really neat thing that we get to do is this operator table thing, where we can call this function on the operator table down here called build expression parser, which takes this table, which specifies all of the operators in our grammar, their order of operator precedence. Negation is higher precedence than product and quotient, while addition and subtraction are lower precedence. And the constructors that we want to use to package up the results of those operations. And that'll generate us a parser which handles all the operator precedence problems that we saw in the last video automatically. And then we're going to call the result of that build expression parser thing expr. We're going to define a thing called full expr, which takes an expr, follows it by an end of file to make sure that we use all of the text in the string. Parsec likes to take string prefixes if you don't tell it that the string has to end. And then we can use all of that, call parse on it, pattern match the right hand of the right of the either. If we get an error, we'll just go ahead and break horribly and crash. But that gives us this parse calc expr function, which we can use to actually parse our expressions. Let me show you an example of that, and then we'll be all set. So if we call parse calc expr on 1 plus 2 times 3, we'll see that we get this syntax tree where it does the multiplication first, and then it adds the result of the multiplication to the 1. Multiplication first, add the result to 1. And everything's working as intended.